This is another interesting question. In this question, we have a wooden plank which is hinged at this point of the tank. The water is filled in the tank up to a height of 0.5 meters and the length of the wooden plank is 1 meters and the specific gravity of the plank is given. We need to find out the angle theta made by the plank with the vertical when the system, that is the plank, is at equilibrium. So let us first draw the forces acting on this plank. This plank is of length 1 meter. So there will be a force of gravity acting on its center of mass in the vertical direction, that is equal to mg. The point of application of the gravitational force is equal to the center of mass of the object. Now there will be another force acting on this object, that is the buoyant force, because it is submerged in a liquid. Now an important point you should remember always is that the point of application of the buoyant force is not the center of mass of the object. The point of application of the buoyant force is the center of mass of the displaced volume. So the displaced volume in this case is this. So the center of mass of this displaced volume is the center of this length, that is somewhere here. This length, let us call it R1, that is this length. R1 is equal to 0.5 upon cos theta. So the center of mass will be at a distance R2 is equal to R1 by 2, that is equal to 0.5 upon 2 cos theta. Now the buoyant force will be acting on the object at this point in the vertical direction, since the buoyant force is always perpendicular to the surface. Now there are no other forces acting on this rod or rather plank. So what we now need to do is that we need to balance the torque due to these forces about this point, so that the object is in equilibrium. Now the torque due to mg acts in the inward direction, whereas the torque due to the buoyant force acts in the outward direction. So these two torques should be equal in magnitude so as to cancel each other. Let us first write the torque due to mg. Let the mass per unit length of plank, mass per unit length of the plank is equal to lambda. Therefore the mass of the whole rod is equal to lambda into 1, that is lambda, because the length of the plank is 1 meters. Therefore the force acting in the downward direction is lambda g. To write down the torque of this force, we have to take F into R perpendicular, where R perpendicular is the perpendicular distance of the line of action of force from this point, that is this distance. So we need to find out this distance now. I'll draw the diagram again. We need to find out this distance, that is R perpendicular. Lambda into g is the force. The R perpendicular is this distance. This was half meter. Therefore this is half cos theta. Therefore this is half sin theta, that is sin theta by 2. Therefore lambda g sin theta by 2 is the torque of mg in the inward direction. This should be equal to the torque of fb in the opposite direction. So we forget the directions, now we just equate the magnitudes. Now the magnitude of buoyant force, magnitude of buoyant force will be equal to the rho liquid into V submerged into G. Now rho liquid is equal to 1000, that is water, into volume submerged. So this volume submerged is equal to, volume submerged can be written as mass upon mass submerged upon density of the plank, that is given to be the specific gravity of the plank is given. So we write this, let this remain as rho L. This is rho of plank into G. Now rho liquid upon rho plank, or rather rho plank upon rho liquid is given to be 0.5. So we can replace this by 0.5 here. The mass submerged is equal to the mass per unit length into this length and this length is equal to 0.5 upon cos theta. Therefore, mass submerged is equal to 0.5 upon cos theta into lambda. So we write this as 0.5 upon cos theta into lambda into 1 upon 0.5 into g, that is equal to lambda g upon cos theta. So this is the magnitude of the buoyant force. We now need to find out lambda g sin theta by 2 is equal to lambda g upon cos theta was the magnitude of the buoyant force. We multiply it by r perpendicular of this force, that is the perpendicular distance of the line of action of this force from the point about which we are applying the equation of torque and finding out torque. So this distance, this being 0.5 by 2 cos theta, this was 0.5 upon cos theta, this is 0.5 upon 2 cos theta, this angle is theta, therefore this will be this quantity into sin theta, therefore we multiply this by sin theta, therefore this is the perpendicular distance of the line of action of FB from this point. So we multiply lambda g upon cos theta by that to get lambda g upon cos theta into 0.5 upon 2 cos theta into sin theta. This is equal to lambda into g sin theta by 2. So sin theta cancels, lambda g cancels, this 0.5 cancels with 2. So we get cos square theta is equal to half. Therefore cos theta is equal to 1 upon root 2 and theta is equal to 45 degree. So our final answer for the angle theta made by the plank with the vertical at equilibrium comes out to be 45 degree. In this question there are certain things you should always remember, that is the point of application of buoyant force is always the center of mass of the displaced volume and not the center of mass of the object.